Thank you so much for having us at this very first Furhat Conference. We are very excited to be here today. And in the next 15 minutes, my colleague Ronald and I will talk about groups, robots and groups, educational scenarios, and nonverbal behaviors. We will try to give you some insight into why we think it is important to study groups and why we think this is particularly interesting in educational scenarios. We will then conclude the talk by giving more details about our most recent work, which was interested in studying how gaze could lead to more balanced participation in groups. And I would like to start by inviting you to think about your everyday life and the different situations you encounter. And you might observe that actually we humans quite often interact in groups. That's at work, in our free time with our friends, but also with our family members. And if we take a closer look at the different groups that we know, then we also might observe that there is quite a few characteristics and processes that define and make or break a group. And cohesion, for example, has been found important to predict group or team performance. And it has also been found among teenagers to be a predictor of more generalized trust towards the society. Since we humans actually interact in groups quite often, we might think this is already enough reason to study how robots could interact in groups. But we like to take it a different or an additional perspective and think of the robot as an assistive tool that can help us to be our best selves. And for groups, that means that the robot can help us to improve the group dynamics that have been found that crucial. For example, it could help to improve cohesion, it could help to tackle conflict, or to include a new member. And for this last point, I want to give an example how we imagine an assistive robot to include a new member. And in this particular work, we invited 3 children, 2 children who were already present in Sweden for quite a while, and 1 child that had only newly arrived to Sweden to play this game. And this game is mostly concerned about placing cubes on the board and making a little bit of music. And the robot's goal was, of course, to help the group to include the newly arrived child. But more specifically, to achieve this, its goal was to establish equal play among the children. Since we couldn't rely on a common language that these children were speaking, the robot had to use nonverbal behaviors to try to establish the equal play. And for that, it first analyzed the situation, how the children were playing, and then it prompted the children to move their cubes on the board in a different way that would foster more interaction and collaboration among them. And in this video, we see how the robot first highlights one cube that should be moved, and then also indicates where the cube should be moved, and then also says that it's very, or like, it doesn't say it, but it's like displaying it that it's very happy that the child moved its cube as the robot had requested. And ideally, we want the robot's behavior to not only influence or shape or help the group in the moment that the robot is present, but also beyond that. And in this experiment, we looked at what happens if we take the robot away after the children had interacted with the robot. And we could see that the children were acting more, especially the newly arrived children were acting more outgoing, and that there was more collaboration among the children. We also saw that the already present children showed more pro-social behavior after they had interacted with the robot.
And this brings us to a specific area where robots can leverage these prosocial behaviors in order to enhance group activities. For example, think about a classroom of students. This is one of the motivations behind testing or using robots in education. A lot of the studies focused on educational robots have usually placed the robot in the role of a peer or of a tutor, and then made some changes on the behavior and the appearance in order to see how this affects the learning process of the student. In most of these cases, the focus target is generally the young audience, so children, for example, and the setting, it's more often a diet configuration where it's a single student interacting with the robot. However, from these results, from these studies, we already know that there are some positive results of introducing robots in education. For example, we know that there is an increase in or an improvement in social emotional states, such as motivation, confidence, or engagement. There's also reports of students who say that they feel less anxious about interacting with a robot than they would do with a human tutor. There's also a positive effect on the cognitive performance of the students, where in a meta study published by Bill Payne and colleagues, they found that the magnitude of this effect was actually very comparable to that of a human tutor. So there's a lot of good results that push us forward in this field of educational robots. But in particular, the task of language learning is very well suited for social robots. And that's because the acquisition of a new language depends a lot of how much interaction you have on that specific language and all of the social cues that you need to apply in learning this new language. And of course, as I've been mentioning, a key way to acquiring the new language is just to practice as much as you can. And these are sort of the characteristics that social robots are very well designed for. While we have already seen studies of robots introduced in language learning activities, these are generally more constrained to practicing grammar or intonation or even learning new vocabulary words. However, and as I mentioned before, the use of a social robot, it's probably better suited to just generating these open activities when students just can practice the new language. And that's one of the objectives that we're looking for in this sort of use of social robots for language learning, where they can guide or control a specific conversation or dialogue in a way that all of the students can practice as much of the new language as they can. This is the specific work that we've been developing here in KTH at the division of TMH, where we are designing this type of dialogues and seeing how we can define the dialogue systems in a social robot to actually generate these environments where the participants can just practice the new language in a very normal way. But in these specific configurations where we have a lot of students trying to speak as much as we can, we're going to have some imbalance in the skills that each of them have. And it's very important that we can design the robot in a way that tries to balance the amount of contribution of these participants. And in particular, we're very interested about how we can use nonverbal behaviors to do so. And we know that nonverbal behavior contain a lot of information in the general communication of humans. So for example, these gestures that I'm doing right now are very informative of what I'm talking about, as well as how I use my gaze or other sort of back channels that I may use between each utterance or expression. In particular, we were very interested in looking at the phenomenon of how a social robot can balance the participation of a group that has a specific imbalance of skill sets only using gaze alone. And we were very interested in this because we have seen how nonverbal behaviors can influence specific characteristics in a group dynamic. So for example, we know that specific gazing patterns can change the participation role in participants of a conversation. So using this information, we designed an adaptive gazing behavior. And our adaptive gazing behavior would read the amount of participation of each participant in the amount of speech, and then adapt to that contribution in the specific activity. So for example, let's think about this scenario where the participant on the left is talking the most. We're going to consider this the dominant participant. If the dominant participant is speaking at this moment, then the robot is going to try to look at both of the participants in equal proportions. However, if the non-dominant participant is talking, then the robot is going to try to look to this specific participant with an extended gazing time. And of course, the gazing time that we assign to this non-dominant participant is computed from the relative amounts of speech from both of the participants. For a study, we used the game Met Andra Ord, which is very similar to the game Taboo, and I guess a lot of people have heard about this game. It basically evolves around a set of players who need to describe a specific word, which is hidden to the rest of the players. And these other players need to guess which word is being described. So for us, we took the robot Furhat as the guesser, and the participants were the ones who needed to describe the specific hidden words. Of course, we wanted to evaluate what happens when you have a specific set of skill imbalance. So we paired a native speaker of Swedish language with a language learner of Swedish, and this was how we tried to formulate or manipulation of this skill imbalance. In addition, we also introduced different word difficulties during the game to see what sort of effect we could also see from this specific implementation.
And while we conducted the study, we compared the adaptive gaze behavior that Ronald just described to a control robot or control gaze behavior. And this control gaze behavior, which we presented in the control condition, was mostly focusing on the speaker, but performing gaze aversion every now and then. Now, to understand how efficient this adaptive gaze behavior would be in balancing the interaction, we first had to understand how balanced is the interaction actually. And for that, we computed how much the group differentiated from the optimal balance, so 50-50% interaction. So we just added up how much each of the members differentiated, or the difference to the balance interaction. And that would mean that if the group didn't interacted quite balanced and the participation behaviors were almost balanced, then this measure would be very low. It would be almost zero. If the interaction was quite imbalanced, then this measure would be very high. Now, Ronald had said that we had 3 different difficulty levels, and we looked at the balance or the interaction balance for each of the different difficulty levels. But it's not only interesting how this changed over a difficulty level, but also since we had the difficulty levels that appeared after each other, this progression over difficulty levels also shows the progression over time. So we first started with the easy level, then we went on to the medium and to the hard level. And we might already visually see that the experimental, so adaptive gaze behavior led to more balanced participation, but we can also say that this was actually significant improvement. And I would like to now go back to the start where I talked about the robot is an assistive tool. And here we think about the robot as an assistant to a group that was imbalanced, but we would still want this group to actually interact balanced. So there's something like in our study, we induced the imbalance by inviting a language learner and a native speaker. And then the robot's gaze was able to overcome this imbalance and lead to more balanced interaction. We can imagine that this might work for all sorts of imbalances that might occur for different reasons, for example, like personality or structural reasons. And whenever we want to balance participation, then this might be useful. So we have been talking now about groups, and I hope you're convinced that it's important to study how robots can interact and improve group dynamics. We hope that you understood why it is particularly challenging in educational scenarios, and we hope that you got some insight into how gaze can balance participation. Thank you so much for listening, and we are very happy to take your questions.